All right, so last chapter. We're into 6:1 today. We're going to talk about systems of equations. And today, we're going to talk about three methods. And all three of these methods are methods you've done before. That's the one thing I think about chapter 6, that it's a good chapter to end on, because we're going to be doing a lot of stuff that you've done before. And that's kind of been this way a lot this year. But systems of equations is something we did all the way going back to Algebra 1. Some of it we even did a little bit in geometry, and then we do it again in Algebra 2. So we've seen this a lot over the years. So we're going to talk about three different methods today. The first method that we're going to talk about is graphing. A system of equations is essentially two equations, or it could be more, but today we're just going to see two. And we want to find the solution to the system. We're also going to talk about what type of systems there are as well. And so the way it's going to look is we're going to have two equations. And we want to solve the system. And so the first method we're going to solve it with is graph. So in order to graph this, first question now I always get is, can we use our calculator? Well, what have I told you all semester? We can definitely use our calculator. Calculator is a great tool to use here. If we're going to put this into our calculator, though, sometimes it'll be in slope-intercept form, but sometimes it won't be. And these are not in slope-intercept form. These are in standard form. So we got to get it into slope-intercept form. So we're going to solve for y. And then on the second one, subtract 3x. So those would be our two equations in y equals mx plus b form. Okay, and I know that you could put this into your calculator right now, and you can use your calculator to help you solve it. But what I will tell you is on the quiz and on the test, you will have some that you have to solve by graphing. So you're going to have to be able to graph it on a coordinate plane, and you got to be pretty accurate, because what we're looking for is where do they cross. The other thing today that I haven't mentioned is we're only going to be dealing with linear equations. So we don't have to worry about quadratics and absolute value and all the different kinds of functions that we've done. These are all linear, so they're all going to make lines, at least for today. I'm going to pull up a piece of graph paper because it'll make this a little bit easier to graph. All right, so the first one was negative x plus 1. We're going to go up 1 on our y-axis. We're going to go down 1, right 1 with our slope. We could also go up 1 and left 1. And you might say, well, why am I putting all those points on there? Well, we don't know where the other line's going to be yet. We haven't graphed the other line yet. And so I would say do enough points where we want to be able to determine where are these going to cross at. Then we're going to connect all our points together. And there's our first line. Okay, the second line was negative 3x plus 7. So we're going to go up 7. That's our y-intercept. Okay, our slope is negative 3 over 1. So from that point, we're going to go down 3, right 1. Down 3, right 1. Okay, and I want to do multiple points until I can kind of figure out where are these going to cross at. So I'm going to go down 1, 2, 3. And now we can kind of see where that line's at. And there's our two graphs. So they do eventually cross, and they cross right here at this ordered pair. And so not only do we want to identify where they cross, we want to know what is the ordered pair where they cross. So right here, I'm going to go right 3 and down 2. So we would say that our ordered pair is 3, negative 2. We call this one solution. Now, the good thing about this is I could take this ordered pair and I could plug it in to the 2 equations that I have, and I can use it to check. If I'm not sure if this really is the ordered pair. That ordered pair is the only ordered pair that works in both of those equations. Okay? And so that's what we're trying to find. What point works or is the solution to both of those equations? The other thing that we're going to talk about today is the type of system. So the solution is one solution. And when I say one solution, for today it's going to be an ordered pair. When I say what type of system do we have here, this is what we call a consistent, independent system. That's not a term we're going to use a ton, so don't freak out too much, because I know that's not something we probably spend a lot of time with. That's the one thing that's going to be a little bit different. But you will have a couple of questions I'll ask you. What type of system do I have? The easy way to remember this is consistent means there's a solution. So that's kind of the way to remember it. Consistent means there's a solution. Independent means the 2 lines are completely independent of one another, which means they're kind of their own thing. They each have their own slope. They have their own y-intercept. They're 2 independent equations. Okay? And so that's kind of the way to remember that. So that's the first type of solution and the first type of system. Probably the most common one that we're going to see, where they cross and make a point. If you wanted to do this in your calculator, once again, not a problem. Remember, you do have an intersect feature on your calculator that you can go to your solve part, you can hit intersect and find out where it's crossing, and you don't even have to find out where it's crossing. Just, if you're going to graph it, then you got to make sure your graphs are pretty accurate, because we want to show that they're crossing at 3, negative 2. All right, second type of system. Once again, maybe it'll be in slope-intercept form, maybe not. This one, pretty easy to get it into slope-intercept form. Same thing over here, add 1. If I were to graph this one, we're going to go down 1. My slope's 2 over 1, so we're going to go up 2, right 1. Okay, I'm not going to be quite as particular with a bunch of points on this one, because what you might notice is that the 2 have the same slope. Okay, and if the 2 lines have the same slope, what's that tell me about the 2 lines? Parallel. Okay, they will not cross. So when I graph the second one, it has a y-intercept of 1. We're going to go up 2 over 1. Connect them together, and there's my 2 lines. Okay, these 2 lines are going to continue on forever, and they will not cross. So it's a little bit different than the last one we did. We don't have to find an ordered pair because there is no ordered pair. So what we say here is that the solution here is no solution. You could use the symbol. It's just a 0 with a slash through it. No solution. And the type of system is inconsistent. Okay. Inconsistent, if you break down the word, the prefix "in" means not, so this just means not consistent. We said just a second ago that consistent means it has a solution, so not consistent means no solution. Just kind of a way to think about the word, because the word, otherwise you're like, okay, what's the difference between these 3? So, trick to kind of remember that. So we don't have to identify an ordered pair there, because there is no ordered pair. There is no point that those 2 lines share. Hey, and then the last one, the last type, Once again, if I want to graph this in my calculator, which if we are graphing, I probably would want to do, this one, you could subtract 2x and divide by negative, but I think an even easier way to do it is add y to this side, subtract 1 from the other side. Okay. You don't have to do any division or anything like that if you were to do it that way. So this would be 2x minus 1 equals y. Over here, trying to get y by itself, so we're going to divide by 3 all the way through. So once again, y equals 2x minus 1. If I were to graph this, right away I notice that my slope and my y-intercept are the same on both. So these two equations, we probably didn't recognize it from the beginning, right? It didn't look like they were the same equation. But when we start to solve it, we realize that they have the same slope, they have the same y-intercept, everything about them is the same. So we're going to go down 1, up 2 over 1. If I were to graph these two lines, they'd be right on top of one another. Exact same line. So two equations, but only one line. So every point that falls on this line is considered to be a solution. So there's a bunch of solutions. And so the way that we say this is infinitely many solutions. I like to abbreviate it IMS for short. Just know what it means. It means lots of points work here. So it's, once again, not just one ordered pair, but a bunch of ordered pairs would work. It's not all real numbers because not everything works. That's different. All real numbers means everything works here, only specific points work. The name for this system is consistent because there are solutions. So consistent means there are solutions. This one, though, is dependent. Dependent means one relies on the other. They have everything about them is the same. They have the same points. They have the same slope. They have the same y-intercept. Everything about those two equations is the same. So those are your three types. Okay, we probably won't do a lot of graphing. There are times where graphing is kind of nice and we can use graphing. But there's going to be other better ways to get out there and do some of this. Okay, second method. Substitution. One variable must be isolated. And what that means is one of the variables has to be by itself. So either the x or the y has to be by itself. And it doesn't matter which one. And I'll show you here in a second which one to choose. Okay, there's my two equations. I'm going to keep kind of today at least go back and keep talking about each of the methods and why do we have the three methods, right? Well, I really wouldn't want to do graphing here. Even if I have my calculator solving this for y, got to subtract 3x, then we got to divide by 5, I'm going to end up getting some fractions or decimals. Don't really want to deal with that. Okay, even if I'm using my calculator, wouldn't be something I'd want to worry about. Okay, so graphing this one, probably not the best method. When we choose or look at substitution here, we want to choose the one that does not have a coefficient. Okay, so the one that we're looking for here is the one that has no coefficient. The one that does not have a coefficient here is the y. It means it doesn't have a number in front. This x has a 3. This y has a 5. This x has a 2. The y doesn't have a number in front. So that's going to be the easiest one, because then I don't have to do any multiplication or division to get by itself. So I'm going to flip-flop, kind of like I did just a second ago. I'm going to add y to this side. I'm going to add 3 to this side. And this becomes 2x plus 3 equals y. Once we have a variable by itself, we're going to take this expression and we're going to plug it in for y over here. We're going to substitute it in. That's why we call it substitution. We're going to take this whole thing and put it in where y is, because those two are equal to each other. Okay? If I told you that y was 4, I could take 4 and plug it in for y. Here it's an entire expression. So we'll go 3x plus 5 times 2x plus 3 equals 2. That gets us down to a single variable. All we have is x's in that equation now. And then we just got to use our algebra skills to solve. Got to do a little bit of distributive property. Combine like terms. Divide by 13. Okay, and once again, you got to remember here, we're looking for a solution. So this is not where we stop. So far, we found out what x is, but now I still have to figure out what y is. And you got some options now. In order to figure out what y is, I could plug it into either of the two originals, or what would be even easier is this guy right here, because y is already by itself. The only issue with plugging it into this is if I made a mistake solving this for y, I might be using an equation that's not correct. But if you feel pretty good about solving it for y, this would by far and away be the easiest one to plug it into. And that's the one I'm going to plug it into here. So I'm going to go y equals 2 times negative 1 plus 3, which is 1. And if you're still unsure of yourself, remember, I can always take this ordered pair. And this wouldn't be a bad idea to do it anyway, is take this ordered pair and check to make sure that it works for both. So if I were to do that, I would go 3 times negative 1 is negative 3, 5 times 1 is 5, negative 3 plus 5 is 2. There it is, okay? If I plug it in here, 2 times negative 1 is negative 2, minus 1, negative 2 minus 1 is negative 3. They both work, okay? That's good news. That's how you can kind of verify, especially on a quiz or test. You can check it right then and there. You don't have to wait for me to grade the quiz or test, because you'll know that you got it right if you check it. Okay, that's the only substitution one I'm going to do. Some of them are going to be a whole lot easier. Some of them already have a variable by itself. Those are even easier. Okay, so I gave you one that was a little bit harder, where we had to do the solving first. But if you've already got x or y by itself, you're ready to go. You can just start with substitution immediately. Okay, the third method is elimination. Okay, I'm going to show you a couple of different elimination types, and once again, why we use elimination. Okay, I'm going to start with a really easy one. What we're looking for here is we're looking for the variable that has the same coefficient but opposite signs. So that one's going to be like a positive 3 and one's going to be a negative 3. And it has to be either the x or the y. Over here doesn't really matter. So right away here, I can see my x's are opposites. One's a positive 3, one's a negative 3. So that's the ones we're going to eliminate. In order to eliminate here, we're ready to go because they're already set up as opposites here. So I'm just going to add these two together. And when I do that, the x's disappear. They eliminate. That's why we call it elimination. X's are gone. And then this would become negative 1y. This becomes negative 1. And we divide by negative 1, and we're pretty quickly to our y value. Here's one of the most common mistakes that people will do. Last one, we solved for x first, and then we solved for y. Here, we found y first. So when you put it into the ordered pair, make sure you put it in for the y value, not the x value. Okay. It's really easy to put it in the wrong place. So we're still trying to find out what x is. Once again, you can use either of the two equations that we started with. You get to choose. I'm going to choose the top one. That's my ordered pair. And once again, I'm not going to show you how to check it every single time, but you could take that ordered pair, you could plug it into both of those equations, and it should work for both if you wanted to verify that. Okay. Why do we use elimination versus graphing or substitution? Well, on this one, graphing it for either equation wouldn't have been a whole lot of fun. We would end up with some fractions or decimals. Even if we're putting it in our calculator, putting it in our calculator with those fractions or decimals would not be a whole lot of fun. Substitution would not be great here because we have coefficients in front of all the variables. Okay, so the first two methods that we did, this one wouldn't be great for either one of those. So that's why I would immediately go to elimination. And that's why we have different methods to get us there. Okay, I'm going to give you one that's a little bit harder. Okay, again, our process or our thought here is we want either the x's to be opposites or the y's. We don't care about this over here. Either the x's or y's have to be opposite. Or right now, I mean, the other one was ready to go, right? It was already opposites. In this case, neither one of them are opposites. So either I need to force the x's to be opposites, or I need to force the y's to be opposites. And you could do it either way. Okay, so you have some choices that you can kind of choose here. Which one are you going to want to go to? Y's or x's? Y's? Yeah, I think so probably too. Because if we did x's, we'd have to go all the way up to 20. So just get a little bit bigger numbers. Okay. With 3 and 2, we can go up to 6, so the numbers aren't quite as big. If you do choose this here, here's where you got to pay attention. Right now they're both positive. So I got to multiply one of these by a positive and one by a negative. Okay, so we're going to make one of these positive 6 and the other one negative 6. So what I'm going to do here is I'm going to multiply the top by 2, not 3. And when you do that, you got to do it all the way through the equation. I'm going to multiply the bottom by negative 3. So we're going to distribute that all the way through the equation. So we got 8x plus 6y. Even the number on the other side of the equal sign has to be multiplied by that. That's probably another thing that gets missed a lot, is people forget to multiply this number. Everything. We got to distribute all the way through. Then we're going to take negative 3, distribute it all the way through. And if we do it right, when we look at our two equations now, they should be opposites, which is what we want. And once they're opposites, now we can add these two equations together. We can get rid of our y's. It won't always be nice integers. We'll have fractions and decimals from time to time. I gave you some examples that work out pretty nice here. Still got to find out what y is, though. So now we got -1 for x. We still want to find out what y is. I probably would go back to one of the two original equations. I'm going to pick the top one again, mainly because it has all positives in it. y equals 5. And that would be our ordered pair. Just remember, if I did choose to graph this one, which probably wouldn't, that's the point where it would cross. You'd have two linear equations and it would cross at -1, 5. All right, one more. At the very beginning of the lesson, when we did graphing, I showed you that most of the time we have one solution, and we've only seen one solution so far other than the graphing. But what happens if I was doing substitution or elimination and I get one solution, no solution, or many solutions? How does it look different? It's usually pretty hard to recognize from the beginning. So if I look at this one and say, oh yeah, that looks like it's infinitely many. There are ways to do it, but I'm not going to really kind of go in depth about that. I would say easiest just to kind of do the work and then see what happens. But in this case here, when I look at these two, I'm just going to solve it like any other. We want either the x's or the y's to eliminate. Okay, so that's where you kind of make your choice about which way you want to go. We can do the same thing we did on the last one, basically. We could multiply this one. Let's multiply this one by -3. And let's multiply this one by +2. One's got to be negative, one's got to be positive, because we want them to be opposites of each other. I always put parentheses around it just so that kind of helps me to remember that I got to distribute it throughout. So I'm going to do it to the top first. Once we get here, we were trying to force the x's to eliminate, right? And watch what happens here. When I add these two equations together, the x's eliminate like I want, but so do the y's. So the x's and y's are both gone. We didn't want that to happen, but that's what happened. So what we have left over here is just 0. Not 0y or 0x, just 0, okay? On the other side, when we add it together, we get -1. Well, we know, hopefully, that 0 is not equal to -1. So this would be a no solution. If I did infinitely many, it would work basically the exact same way, except everything would cross off. If I had a -21 here and a +21 here, those would also disappear. Everything would be gone, and that means the two equations are exactly the same. Okay, so that's really the only difference between the no solution and the many solutions. I won't go through an entire example of infinitely many solutions, but they look similar, but just slightly different on are they equal to each other or are they not equal to each other. Okay, you guys kind of remember all this stuff? It's one of those topics that I think we probably spend more time on this than almost anything else that we do. That's kind of why I like ending on this chapter, because hopefully we have pretty good background knowledge of a lot of these things. And really the whole chapter here is going to be talking about solving systems different ways. Now we're going to eventually get into some story problems and some of those kind of things, everybody's favorite, but we're going to talk about other ways to solve as well. Okay, these three are graphing problems. it says that as well. But if you want a piece of graph paper, I got some on the counter over there. You can grab some if you want. And then the directions pretty much tell you what method to use, substitution or elimination. If there might be some, I can't remember if there is or not. I know there's some in the section, I just can't remember if I assigned them, where it says choose whatever method you want to solve. We'll see some like that at some point, and you can kind of choose what method you want to solve if it doesn't say what method to use. But I will tell you next week on the quiz, if it says solve by substitution, then I'm going to be looking for the work to do substitution. Or if it says solve by elimination, I'm going to be looking for the work for elimination to solve by those specific methods. Tomorrow,